All right, thank you everyone. Good afternoon, and thank you, Philip, for the nice introduction. Um, I'm going to talk today on behalf of GEOS development team on next generation simulation tools for CCS. And I think our main goal with GEOS is bridging coupled physics and high performance computing. That's the message that I really want to share with you today. And this is essentially the roadmap that we are headed today. So I will place this question as a motivation and elaborate a bit more on why we need these HPC simulators. Give you an overview of the architectural design of GEOS. And then I will move to some numerical examples. First, a discrete matrix, fractal matrix example, and a sequence of large-scale simulations. And finally, a conclusion and future work, where are we heading with GEOS? Okay, so I think to answer this question of why do we need a HPC reservoir simulator, what it comes to my mind is thinking about in the upstream subsurface, we have a lot of experience in the oil and gas technology that we can leverage on expand CO2 storage and the operation of CO2 storage sites. But despite that, I think the main bottleneck for CO2 storage is that there is a large demand on expanding not only the spatial scale, but also the time scale. So we have a call for larger simulations, essentially. So we need infrastructure that can cope with this. And the idea is, in order to solve physics at large scales and with complex, let's say, coupling, we need a design for a simulator that can couple with this. So if we look, let's say in the first block, there are some items that if you look in the, let's say, open source simulation market and the commercial simulation market, there are let's say, tools that can cope with complex fluid thermodynamics, let's say, coupled physical process, resolving either fine spatial scales or time scales. But in the best of our knowledge, there is not a unique tool or such a tool that can cope with all at once. So where we come from is actually starting from the design of a HPC infrastructure that are scalable and portable at the same time, and also can cope with multiphysics with no performance bottlenecks. And our answer to that kind of question is GEOS, which is an effort of multiple institutions in the US. Two institutions are academic, which is the Lawrence Livermore National Lab and Stanford University, and Total Energies from the industrial point. The industrial side. So if just to give you an idea what Livermore brings to this interaction is years of research on development and HPC, let's say, experience, and also geomechanics at the scale. And Stanford offers more than 40 years on development of simulation technology and 20 years on the development of ADGPRS, which is an in-house reservoir simulator. And Total Energies, on the other hand, is in charge of development or deployment or development of simulation cases, scientific computing, and also addressing client needs. So you can see this is a huge collaborative effort. As such, you can see a list of many names here, and it's still a short list, just to give you an idea how large is this project and how the interactions are. Now let's move to a short description of what is GEOS. So GEOS is an open source simulation framework that, if you allow me to express it in this way, is composed of 5 levels of abstractions. The first level of abstraction is kind of the portability layer that allow you to execute code in parallel with different policies and move between different spaces. memory spaces. I will elaborate a bit more on that in the next slide. So there is a layer of computational infrastructure that handles data repository internally, the mesh, MPI communications, the input and output of files, and the event management, because GEOS is an event-oriented tool. So we have a layer of numerical methods, finite elements, finite volumes, and the polyhedral counterparts, virtual elements, and mimetic finite difference. And I will explain a bit more on that. And we have, of course, a layer of constitutive laws, physics solvers that we can use to ultimately create large linear systems that we need to solve with a linear solver. So that's why we need a final layer of linear algebra to combine, let's say, so GEOS is a combination of these layers. Now, if you allow me to give you some more details about the portability layer that I think is really crucial if you want to engage with these kind of designs. First, you need a library or an abstraction that allows you to decide how to execute, let's say, a for loop in parallel and how you want to handle the data. So this execution model is provided, or this abstraction is provided by Raja, which is a library designing with that purpose. And then there is, what comes out with the memory management, there is the layer of, let's say, Shai and Empire, which is kind of two libraries that combine, allow you to create a notion of multidimensional array that we call LV array. I think the word picture is the following. So once, for those that are familiar with discretization of PDEs, normally you want to start by a notion of a vector, right? And then when you think in like large-scale simulators, this vector needs to be distributed. So LV array is kind of that abstraction that allows you to code without thinking that you need to distribute. And also, the natural extension is to create a matrix. And therefore, the matrix is already distributed. So this portability layer is quite important. Now, in terms of physics solvers, of course, we have single physics that can be combined to, let's say, construct multi-physics solvers. I think the message that I want to convey here is that each discretization has different requirements, because some of discretizations support degrees of freedom on nodes, on edges, on facets, while others are more facet-based or volume-based. And any combination of these solvers is not trivial. You need to do it carefully, because there are underlying mathematical principles that require that the combination of functional space at that level needs to be stable. I don't want to discuss this in detail, but I'm really happy to discuss that if someone had questions on this topic. Now, in terms of discretization, this is what I want to convey here. We not only support standard cells like hexahedral, TETs, prismatic, let's say, forms or pyramids, but also we extend the notion of continued Galerkin finite elements via virtual elements to polyhedral cells. And for the flow problem, we can have a TPFA construction that can also be represented or extended to polyhedral discretizations under underlying mimetic operators. So I like to say that this parity is beautiful in the sense that you extend the standard discretizations to polyhedral meshes for mechanics and for flow. And this is essentially giving you a more flexible geometry description in your framework. And now let's move to numerical experiments. So the first is a discrete fracture matrix example. Let me just say that in this example, I took this geometry from a well-known benchmark in this reference, where these benchmarks were designed to test different discretization techniques for the flow problem of DFN, let's say, discretizations. And the benchmarks elaborate on complexity from 1 to 4, and this is actually the most complex case, which is 52 fractures with different shapes. As you can see, some of the fractures are kind of circular, some other are elliptic, some other are a portion that are rectangular. But the point here is that they are intersecting in a complex manner. So here, this example is still academic, but the message that I want to convey is that if you put a mechanics operator on top on this discretization, you will have flow and mechanics interacted in a complex manner, even in this simple setting. So the setting is very simple. You essentially set up a permeability of 1 in the matrix and 2 order of magnitude in the fracture, because essentially one just to say that the permeability in the fractures are higher. We apply a compressional load on the body of 20 megapascal in each direction, including all the fractures. And we have an injection configuration that the solution, the expected solution, is a pressure field bounded by 10 and 30 megapascals. So from the mechanics, you expect to solve contact mechanics equations, but since there is no shear in this aspect, we only look to the normal components of the traction. So in order to solve the contact mechanics equations, I'm not going to describe all the equations in detail, but essentially we need to solve for some KKT conditions, and they look like this in the normal direction. And what is interesting for this setting, and I just want to show that GEOS across refinements are not only consistent, but preserve some properties of the scheme in terms of iterations and physical, let's say, meaning. So in this setting, we can just derive a level set function where this term essentially vanishes at the solution, because in the augmented Lagrangian discretization, this penalty term is updated during the iteration process, and essentially it decreases. So this term is vanishing. The Biot coefficient in this setting is 1, because we are talking about the fracture, and therefore what we are looking is just the simple balance of two forces. And then when we look into the solution of this, you see on the left, on your right, the solution on the matrix. On the left, the solution on the right, the solution on the fractures. And you see on top the pressure solution. At bottom, you see the stress and the traction solution. And this is for the original mesh resolution. So if you really look into the normal traction, and as I said, you look into the level set function, so whenever the pressure is exceeding 20 megapascals, the fracture will open. So therefore, the expected traction or normal traction is 0. So if you see the pressure is bounded between 30 here and somewhere 10 megapascal. So somewhere the pressure here is exceeding that limit, so you expect these fractures to be open. And as the level set move to the, let's say, the lower pressure zone, the fractures are closed. And since we are using GEOS, we can refine, and you can see that the solution preserves their features and is essentially converging. And the point here is that we start from 0.1 million to 30 million in two refinements. And this problem is fairly easy to solve in a machine that at least can accommodate 40 gigas of RAM. So you can, if this computer has that property, we can run this in this machine. Now, let's talk about something more interesting, large-scale simulations. But before that, I'm going just to express that we run some experiments on these clusters that has clearly different kind of processing units. The first is CPU based. The next one are GPU based. They are from different manufacturers, and they have different number of nodes available. And then for the next numerical example, we exercise in these two machines, and for the last numerical example, we exercise on this machine. Okay, so this first example is essentially a section of the Northern Lights project. I'm not going to elaborate on the original settings because I'm sure you are really familiar with this project, and I think it's not really, without neglecting the importance of that, and for the sake of time, I'm just going to say that the region is simulated around the injection point, but you clearly see that there are features that extend beyond that. So this is kind of resonated with the idea that there is a demand for simulating largest domain, right? So in this setting, we can see that the mesh is already intended to model the mechanics components. So we have an overburden and underburden region. So we have the reservoir in the middle, and we have, of course, you can see some kind of a structure mesh, but also there is a layer of tetrahedral represented, let's say, non-trivial geometries like fold geometries that bend, and there is a layer of pyramids connecting the layers. So we have a full conformal mesh that it gives you around 16.3 million degrees of freedom for the full couple setting. And this is multi-phase poromechanics. Now, this is just a snapshot of the simulation at 25 years, representing the CO2 plume. But beyond that, I really want to show, in terms of data, why is actually GEOS is portable and scalable. I think the portability is already clear by saying that since we run the code in these two different machines, one is CPU, the other is GPU-based, the thing here is that you write the code once, and then you compile in the different machines, and that's all. That's the only thing that you need to do. Now, of course, you need to have the resources for that. Another important feature to say is that if you look, for instance, to this, the first machine, the Quartz, we can effectively reduce the time from perhaps 3.8 hours to maybe 36, 37 minutes. And this is kind of saying that it has a strong scalability. Of course, it's not perfect, but we are constantly improving this. And in terms of GPU, in this case, the scalability is not really perfect, but these results were generated 2 years ago. So we already improved this situation here. Another important thing to observe in these numerical results or statistics is that if you look into the Newton iterations per time step and the GM-res iterations per Newton iteration, they remain fairly constant. And this means that you have a fixed size problem and you just keep adding resources to solve it, let's say, to get the solution faster and faster. So while having a constant number of iterations, this means that all the numerical features of the discretization, the stiffness of the operator should remain the same. So therefore, the number of iterations should remain the same, right? So this, if your code is correctly implemented. So this signified that the code has been created to preserve these properties. And also tells you that the code is correctly implemented in a way. Now, if we move to a weak scalability case, so for these results, let me just go back, just to recall. I'm going to present results for this machine, which is GPU-based. So in this result, the scenario is different. Is compositional poromechanics, non-isothermal, on a setting that we can actually refine. Like we have full control on the refinement. And the setting is simple. We inject CO2 in this region, which is, the red is a permeable layer surrounded by an impervious layer, which is the blue one. This is essentially the domains, the dimensions of the domain. And on the right, you can see that when we start from a mesh level 1, we have 3.2 million of degrees of freedom until 1.6 billion, if we just go 10 levels of refinement. And how it looks in terms of, let's say, scalability. So if we just measure the time for the setup of the linear solve, the actual solve time and the iteration time during the solution. Ideally, you should expect these lines to be flat. It's fairly flat, so this is actually a good scalability result. So what you see at the bottom is that we refine the domain and we add more resources. So this is essentially telling you that you spend fairly more or less the same time by solving the problem, a smaller problem with this level of refinement and 2 MPR ranks, compared with, let's say, the level 10, that is 1.6 million. So this is, in a way, a good result because it allows you to predict how many resources you need to allocate when you just trigger this process in the cluster. Okay. I think for the sake of time, I'm going just to say that this example is also to say that we want also to show that GEOS compare with others, let's say groups, and other simulation tools that are out there. So we submit results for the SP11, and in particular, we exercise the SP11C, and internally we run even further refinement from more than what's required, actually. And so I'm going just to skip that, but the message here is telling you that we compare fairly well with other well-established simulation tools. And let me just move to the conclusions. So I can conclude that I think it's fairly okay saying that for CO2 at large scale, we need high performance simulation tools. I think GEOS is a potential solution because it's portable and it's open source, so you can see every piece of Linux code and what is exactly the code doing. And also we have demonstrated that GEOS is an effective and scalable tool. Not, essentially for CCS, but also for geomechanics and complex fracture settings. And now the roadmap is essentially continuing improving the scalability and the efficiency. And I would like to say that we envision GEOS to be a reference simulator tool for the community with validated workflows and benchmark cases. And also we envision to integrate AI-driven tools to speed up the simulation setup and the post-processing analysis of results. And these are the reference, And I also want to acknowledge the effort of the development team. I would like to acknowledge Total Energies for all the simulation cases that they provide and all the simulation technology that they also contribute. The US Department of Energy, because across different projects during the lifespan of GEOS, has been generously funding the project. These are the reference, and with that, I'm going to stop here. Thank you so much.